Welcome. This is the first of the asynchronous lectures for the final week of Discover Geography. And in these three lectures, I'm going to be introducing the issue of climate change in relation to humans and the environment. And remember, this last week, what we're really talking about is how humans, from the standpoint of geography, interact with our environment. Remember that we had talked already about when we understand broadly issues of humans and the environment and environmental change, we're often talking about the question of extent, that is, geographically how big an area is, the magnitude of the change, that is, how much something is changing, and then lastly, rate, how rapidly something is changing. And so when we look at climate change, these are the issues that I want you to kind of consider. In the first lecture, we're going to talk about what we mean by climate and how we understand its parameters as they relate to Earth and Earth environment. So let's get started. So lecture number 1 is Earth's climate. And first of all, we have to start with what do we mean by climate? And then we're going to talk a little bit about what drives climate, and that would be energy and how it interacts with the atmosphere. And then lastly, we're going to talk a little bit about greenhouse gases, what they are and why they do what they do. In lecture 2, we're going to talk a little bit about climate change, that is, how climate has changed through time, what we think is happening right now, and how that affects humans and the environment. The last lecture, we will be looking at the ideas of mitigation and adaptation, that is, how do human beings respond to climate change. All right, so let's get started. When we say climate, what we're talking about is the weather conditions for a location averaged over some period of time, and then we often also include in climate those extremes in weather behavior during that same time period. So one way we often hear this is climate is what you expect. In other words, what the average is. And then, of course, what we get on a given day, week, or month is weather. All right, so the other way of thinking about this is it is an envelope of possibilities. In other words, if you think about the average of something, that is the envelope of possibilities in which weather kind of bounces around. So again, right now, whether we expect it's late November, we expect our temperatures to be in the low 40s. Now, it doesn't mean that we might have a day that's significantly colder or we might have a really nice day, but it's that kind of average. The other thing that we often talk about is that we tend to look at climate in 30-year averages. Now, sometimes we use longer data sets, but in general, it's that 30-year average. And again, we're mostly looking at temperatures and precipitation. Although, again, we will sometimes include things like frequencies of severe weather events. That can include drought, it can include hurricanes or tropical storms, and it can also include severe events such as tornadoes. All right, so let's take a look at what we call a climograph. Now, a climograph, and again, I want you to focus on several components of this. This is a climograph, and what we notice on the bottom, the horizontal axis is time, and this is months, so January, February, March, April, May, June, July, August, etc. Then on the left side, we have degrees, temperature in Celsius, again, from 0 here, the baseline, up to 50 degrees Celsius, and then down to -20. On the right side, we have precipitation totals in millimeters. Now, degrees Celsius is the monthly average temperature, so the average temperature recorded over the entire month. The precipitation is a total. And what we can see, this is going back, this is Ontario, Canada, and notice that it's the average. Remember I said climate is a 30-year average. So this is taken from 1909 to 1939. And what we see if we look at this, so again, I'm going to start with precipitation. And what you'll notice is that our highest precipitation month here is July, drops a little bit, and then we have again September, October, fairly high. But that late summer is the highest amount of total precipitation, and the lowest occurs in February. Now, we can also see temperature, and you'll notice here's our temperature line. Our lowest temperatures are January and February, and then temperature climbs towards the summer. Right? So that is what Alsace, Ontario was like between 1909 and 1939. In other words, that's what we expect. Now, if we go forward in time, one of the things, and I'm going to kind of go back and forth here a couple times. So 1939 and then 2000 to 2019. Now, a little bit shorter window. But what you'll notice if I keep toggling back and forth is that we've seen that precipitation has gone up, as has temperature. The overall trends are very similar. But in this period of time, again, from essentially 1909 forward, so about a 90-year period, we see that these parameters have climbed up. Temperature's gone up, and then so has precipitation. Now, you'll notice here, the temperature mean is 1.6 degrees Celsius, and now the temperature mean is 0.5. And so we often talk about this, what is the change in the climate, the temperature parameter over that time. And you'll notice in the case of Elsa's, it's right at 1.1 degrees Celsius over this last roughly century. All right, let's look at somewhere else. So now we're in Washington, Pennsylvania. Some of you are familiar with this area. It's right around here. And again, we want to look at the parameters. First of all, again, if we look here, we can see we have the same parts of our climograph. Again, so here's our temperature in degrees Celsius. Here's our 0 line. Again, for those of you that are Fahrenheit, this is 32 degrees Fahrenheit, and this is about 70 up here. And so, actually, I'm sorry, about 70 here. So what we can see again in our temperature in Washington, again, which is very close here, again, our low temperatures are here January to February, and then our temperatures come up into the 70s, about here, and then they go back down. So again, that's our curve, again, 1909 to 1939. Our precipitation in this area centers in the center of the summer, and we also have a fairly high amount of precipitation and snowfall here in January. So again, this is our historic climate. If we move forward, again, our average temperature here, 10 degrees Celsius, and our total precipitation for the year is 1,016 millimeters, or roughly a meter. Now, again, what we see, we move forward, and again, I want to point out these values, 1909 to 1939, and then 2000 to 2019. What we see in both cases is that we're seeing a change in both our parameters in the upward direction. Our temperature, again, today, the average over the last 20 years, is 11 degrees Celsius, and if we go back in time, it was 10.5. So here we've raised 0.6 degrees Celsius. Now remember, Ontario, higher change in temperature, but also higher latitude, and it's worth remembering that. So climate changes over time, and in these two locations we see that temperature is going up, as is precipitation. Now, why? How does climate work? Well, at the most basic level, climate is driven, and this is really both precipitation and temperature, are driven by energy from the sun. Energy from the sun, incoming solar radiation, gets to Earth, and then it has to interact with the atmosphere first. And a couple of different things can happen. Incoming solar radiation can be reflected, and some of that energy is in fact reflected. Some of it is reflected by clouds. That's why, in fact, the tops of clouds actually look white. And then some of it is actually simply reflected by the Earth's surface. Snow, water, certain types of materials simply reflect solar energy, sunlight. But a significant portion of it, roughly half of it, is actually absorbed by Earth's surface, and that is either land or oceans. Now, energy coming in, we conceive of as light, although it's a whole wide range of spectra. But it's coming in as shortwave energy. That is very high energy. When it is absorbed, it is converted from shortwave energy, shortwave radiation, to longwave radiation, and that's thermal or heat. Now, that is Earth's surface, and again, if you ever walked across sand in the summer, your feet get hot. That is sunlight converted to thermal radiation. Now, what happens then? Well, it is emitted. In other words, Earth also emits energy. It just emits it in long-wave radiation. And most of that is radiated out to space. from, again, the atmosphere, the Earth. Okay, so if we think about this, energy comes in, and we have that energy being emitted. Now, some of it goes directly into space, but not a whole lot. Some of it goes into the atmosphere and heats the atmosphere. Clouds, etc., absorb that energy. Okay? And then some of it is re-radiated back down to the surface. So we have a dynamic energy budget. And the question of how much gets through and how much gets emitted is a function of our atmospheric composition. So in other words, what the atmosphere is made up of influences how much energy moves into it and how much energy moves out of it. Now, right here we can talk a little bit about this, and you'll notice that we have lots of things in here that are about clouds. Water vapor in the atmosphere strongly influences how much energy comes in and how much energy goes out. So, again, let's take the first half of this. Solar radiation comes in, incoming solar radiation. Some of it is absorbed by the atmosphere, and the atmosphere heats up. Some of it is reflected by clouds, and again, some of that energy reaches Earth's surface. Some of that which reaches the Earth's surface is simply reflected. But again, some of it is absorbed. So absorption means we're changing solar radiation to thermal radiation. Now, goes the other way too. Outgoing long wave. Incoming is short wave, outgoing is long wave. Outgoing long wave radiation is emitted from the surface and from atmospheric molecules. Okay, so again, surface emits. And again, if you've ever walked on hot sand or hot asphalt, you know that there's heat coming off of that. The thing is, if you look right here, this is the critical part of what keeps Earth warm. Sunlight comes in, is converted to long-wave radiation, and that radiation is emitted. But a lot of it is captured, if you will, in the lower atmosphere and re-radiated back downward. In a sense, keeping Earth warm. If all of that energy just went back out to space, every time we went to night, Earth would get radically colder. Okay, away from the sun, it would get extremely cold. What makes this work is, in fact, what we call the greenhouse effect. Okay, so the greenhouse effect is the balance between this energy in and the energy out. The important idea is, depending on what the atmosphere is composed of, more heat is retained. We need that heat to be retained for Earth to be habitable. Now, what does that? Well, the atmosphere contains what we call greenhouse gases. And the idea here is not that this is intrinsically bad. In fact, it's necessary. But the amount of these gases determines how much energy stays in the system and for how long. So what are greenhouse gases? Again, if we think about it as, if you will, kind of a blanket on Earth. Ultraviolet or shortwave radiation comes in, and infrared or thermal radiation goes out. Well, that balance has to occur, and what often happens is, depending on what the atmosphere is made up of, some of that infrared radiation, long wave, gets re-radiated back down. It kind of bounces around in here. If we add two gases to our atmosphere, and we're just going to talk about these two for the moment, carbon dioxide and methane. These are two examples. Some of these, if we have a small quantity of them, some of the energy keeps re-radiating back. And if we go back 1,000 years, 10,000 years, the quantity of both of these was more or less at a point where the temperatures were what they were. Okay? Now, what happens, though, is human beings came along, and especially during the industrial age, and we started adding more carbon dioxide and, to a degree, more methane, although the methane was oftentimes from different sources, especially animal production. Well, as soon as we add more of these, more re-radiation from the atmosphere begins to occur, and the atmosphere begins to heat up. We add a little bit more, and even more of this energy is trapped, and the atmosphere heats up. The more we add of these, the more radiation, long-wave radiation, in a sense, bounces around in the atmosphere, is emitted from their surface and then re-radiated back down. That's the greenhouse effect. Now, what are the greenhouse gases? And again, you do need to know this for the exam. Carbon dioxide, which again, all respiration produces, so people breathing, animals breathing, anybody breathing produces carbon dioxide. Methane, which comes from both the extraction of fossil fuels and from animals. And then we have nitrous oxides, water vapor, and ozone, and chlorofluorocarbons. So these are our main ones. Now, when we talk about these, though, greenhouse gases, so again, carbon dioxide, methane, chlorofluorocarbons, nitrous oxide, water, and ozone. What we have to understand is that they don't all act the same. If we look at them, oftentimes what we talk about is global warming potential. And again, global warming potential is a measure of how much heat in a greenhouse gas traps in the atmosphere relative to carbon dioxide. We use carbon dioxide as, in a sense, 1. It's our index. And so what you'll notice here is that global warming potential for carbon dioxide is 1. In a sense, methane has 72 times the greenhouse gas potential as carbon dioxide over 20 years, over roughly a 20-year period, because it stays in the atmosphere for a moderately long time. Now, the nitrous oxides are even more significant, almost 300 times the impact of carbon dioxide. So while we focus on carbon dioxide because it's the largest thing that we emit, there are other gases that are of also significant concern. Okay, we're going to stop there on lecture 1. Again, the main ideas: what is climate, the components of a climograph, so we can read that, and then greenhouse gases and the greenhouse gas effect, or the greenhouse effect. All right, we'll see you in the next lecture.